Terrible. Okay. Okay. Sorry to the video. You missed the motivation. Oh well. Okay. So, but there's a big question here. So which is like, how do we? Yeah. And the other thing about this is that these results, or some of these results, hinge crucially on thinking about quantum field theory from an operator algebra point of view. So that means doing algebraic quantum field theory effectively. And so, I'd like to be able to do algebraic quantum field theory in the bulk of ADS-CFT, and I don't know if I can do that. And so part of this is trying to push the limits to see if I can do that. Okay, so in particular, I'll be talking about types of non-nominal algebras. I won't say too much about it. I'll just use the jargon, but it's not that, let me demystify it very quickly. In local quantum field theory, we think about algebras associated to local regions. So there's some causally complete region, say for example a diamond, like this, O. And then there's some operators that describe that region. And this is typically, this is always, you can prove that it's always a type 3 one binomial algebra with maybe some extra assumptions on the quantum field theory, but for reasonable quantum field theories, that's true. And why is this coming about? What does this really mean? Well, it's coming about from sort of infinite amount of entanglement near the cuts here, right? So near this boundary of this region, there's an infinite amount of entanglement, which means that any state in the quantum field theory Hilbert space has infinite entropy. And that's a property of these type 3 one binomial algebras. So that's one, and then we should contrast that with just quantum mechanics that we usually think about, say, quantum information theory, which is often just type 1, okay? So type 1, a good example of type 1 algebra is just bounded operators on some Hilbert space. Okay, so what I'm trying to do is push, in particular, quantum error correction, our quantum error correction picture of holography, to a regime where we can have these sort of type 3 von Neumann algebras in the bulk. Okay, and so we already heard a talk about that, but that's good. So other people are thinking about it. Okay. Now, however, if you talk to Daniel or Ahmed, and they tell you what is this quantum error correction in ADS-CFT, what is this story? Well, the first order thing they'll tell you is that, okay, maybe we have some ADS-CFT set up, we have some boundary regions that I'll describe with algebras, and I'll call M and M prime. And there's some RT surface in the bulk, and then there's some bulk regions. And then, we can think about doing error correction in the bulk if we have some bulk algebras, N and N prime. But in the simplest setting of this error correction, you always take N to be small. So N is small. And I mean really small, from my point of view. It's a finite dimensional Hilbert space. It's just a finite number of degrees of freedom. And that's at least the best setting for where we understand things. So we have, in terms of this type classification, we can still have M prime being type 3 on the boundary, because they're boundary regions with one of these endpoints, just like here. So they have infinite entanglement, they're type 1. But then N and N prime are just type 1. Type 1. Okay. But okay, so this is not great for my purposes. So yeah. So however, there were some results, and Monica already talked about these, and I did some work from last year, from 2 years ago, where we sort of pushed this, and we did realize settings where indeed you can push this, push the limits. Okay, I don't know why I did that. Where now suddenly you have this setup where you have type 3 in the bulk. Okay, so this is what you get. N is type 3, and N prime is type 3. Okay, that's great. So you can do it, but there's some issues. So the first issue is that it's exact error correction where it works. Well, it works sort of obviously. And so we don't expect exact error correction in the gravitational theory. We expect there to be errors. So we should somehow try to build that in. And it turns out that that's kind of a hard thing to do. Okay, there are some basic issues with that. But another issue, and this is something that was always in the back of my mind, is if we think about this duality at finite g Newton, let's say finite but very, very small g Newton, then there's a sense in which the type 3-ness of the algebra in the bulk is not because of some RT surface here. Right, so you have some RT surface here, and you maybe think because this is some local region, just like in this setup here, you have infinite entanglement over here. If this really was quantum field theory in the bulk, then you would have that. But we know if g Newton is finite, then that should actually be a finite entropy. So what does that mean in this setup? Well, it means the type 3-ness is coming from the boundary, right? So some UV divergence at the boundary. And so it's not really what we want, okay? And so we can push this further. So to see this sort of issue further, we can think about a more sort of the most interesting code, or a more interesting code, where we have a black hole.
Tom?
Yes.
Just in terms of motivation, I'm a little bit confused. As you just said, in the bulk, it isn't really type 3 anyway. So why are we trying to get that?
Well, I still want to get that. I'm stubborn. Let me put it that way. So I still want to get that because I want to apply these results about energy conditions, or at least see them, how they arise in the duality.
But you don't mean, you want to get it in the limit as n goes to infinity.
That's exactly what I'm going to say, yes. That's the punchline, yeah. I'm going to get it in the limit n goes to infinity. Right now, I'm not thinking about that.
Oh,
yes.
sorry.
Yes. So if we still stick with this sort of limit where we're in small g Newton, we can think about sort of the thermophile double state, which we know above the Hawking-Page transition is dual to some two-sided black hole, eternal black hole, with some horizon, given by this time slice. And in this case, we can sort of think about error correction here. Maybe we have some boundary algebra here, m on the left, m on the right. Then we have some bulk algebras, n on the right, n on the left. And then in this case, because g Newton is finite, this is just a type 1 algebra. This is just bounded operators on the Hilbert space of the CFT of the right. Okay, so that's by definition type 1. And then it would be really weird if this was not type 1 as well. Right? So this will be type 1. And that's not really what I want. So this is just making this paradox stronger, or not this paradox, or just this fact stronger. Okay, but now, fast forward to the end of last year, there was some interesting work by Lou and Luthauser, Sam, who's in the audience, who gave a nice talk, who proposed a way that you can get these type 3 von Neumann algebras where this type 3-ness in the bulk is really coming from this surface, or in this case, there really is a type 3 von Neumann algebra, as long as I take the strict n to infinity limit. Okay? So that's what I'm going to try to do. So I'm going to try to do that. Of course, they did that, but I'm going to try to do that. I'm going to try to sort of directly confront this and try to put it in the language of error correction. Okay? Okay, so I'm going to directly confront the large n limit. Okay, so that is the motivation. Let's get going. So to set up this formalism, I need some structure. So let me introduce some structure, some assumptions about the system that I'm working with. Okay, so the first thing is I need a theory that I'm studying. So what do I need? Well, favorably, I want a sequence of CFTs that are labeled by some parameter n, which is the n of large n. So n is just going to be an integer. But to be a little bit more specific, what do I want? Well, this CFT is going to act on some Hilbert space that I'll call kappa n. And so this is my boundary Hilbert space. This CFT I'm going to take to live on the cylinder for simplicity. So here's a cylinder, and it's in any dimensions. So this is R SD minus 1. And I'm going to think of it from an algebraic quantum field theory point of view. Okay. So that sounds scary, but I'm not going to think of it as being scary. So all I mean is that on this boundary cylinder, I'm going to have a bunch of causal diamonds. And I'm going to call these causal diamonds, following the literature, O, which is a really unfortunate labeling, but I'm just going to go with it. Because it looks like an operator, but it's not an operator. It's a causally complete open region on the boundary. And maybe there's more, of course there's more of these, O1, O2, and there's a whole bunch of these, and they don't have to be just these wedge-like regions, they could be multiple regions or anything. But there's some family of these, and I'll call this family of O just K. And algebraic quantum field theory is just an assignment of operator algebras that act on this Hilbert space to these local regions. So it's an assignment, so basically it's a map, Mn of O. So this is the algebra associated to that region. That's the algebra in the CFT associated to that region. And this is just a map from K to Mn, where Mn are all of these algebras together. And for me, all of these algebras together is just going to be everything. So it's just bounded operators on that Hilbert space. Okay? So this is my setting. I have causally complete regions, and I have assigned to them these von Neumann algebras. Okay, good. Okay, so these things are going to have all the nice properties that we want, right? So that we'd expect. So these have nice properties, and I'm not going to list them just because they're kind of obvious. Or many of them are obvious, but I am going to list just a few. So the first thing that I'm going to focus on here is this property that Mn for some region O, and Monica already mentioned this. So if I take O and I think about O prime, so what is that? Well, O is some causally complete region. O prime is just the complement of that. So it's this region on the cylinder, if you like. So this is O prime, and this is O. Right. So it's also a causally complete region, but it's space-like separated to O. Okay? And so if I think about algebras in the complement region, they should be equal to Mn in the original region commutant. So this prime, the prime in terms of the space-time region is this operation. The prime in terms of the algebra is the commutant. And that just means take all the operators in this bounded Hilbert in B of K that commute with those operators. Okay? So this property is called Hague duality, and it's kind of important. If you just imposed causality, that the theory satisfies causality, you would just have this inclusion, and then that would satisfy causality, so that's a completely reasonable thing. Hague duality is basically saying that that's somehow maximal. So the theory is maximal with respect to that causality. Okay? And it's something that you basically would always put in if you're thinking about this quantum field theory as some regularized quantum field theory on a lattice or something. You would have this. So there's that. And then, the other things that I need, the CFT has symmetries, so I'll impose those. And yeah, and that's basically it. Okay, so that's my starting point, so this sequence of CFTs. Now, if I just had an arbitrary set of CFTs, that wouldn't be very interesting. I have to have some way to relate the different CFTs for different n. So how am I going to do that? Again, a lot of this is sort of following this paper here, but sort of putting it in equations, if you like. So so to take the large n limit, I have to think about the single trace algebra. So what is that? Well, it's going to be a set of local fields, alpha, that sort of have a nice large n limit. So in particular, they have the property that they're defined in each n of the theory. So for any CFT, any of this n, you tell me, if I give you one of these single trace operators here, I can give you a representative of that in the finite n theory. Okay, so this is the sort of, if you like, this set is like the infinite n single trace theory, single trace sector. And I messed up my, yeah, that's okay. So this is, yeah, so the infinite n single trace sector, and then associated to each of those, I can find a sort of representative in each n theory. So for example, so in the n theory, so there's some operator, phi alpha bracket n, which is just some trace over matrices, say if it's a matrix theory, like this. Okay? Right, and then I started with, in the n is equal to infinite theory, just this set of operators. Okay. And so the structure that I'm going to advocate is a map between these two. So it's a map going this way. I'll call the map gamma n. And it basically takes the single trace algebra to a representative in the finite n theory. Okay. Now, you know, one important thing is that this will be an algebra. It will, go on.
Sorry. Maybe you'll talk about this, but this algebra you're describing, I would have thought that it would, for some generic state, it would land you on, and a generic subregion, it would land you on the causal wedge and not the RT surface.
You're anticipating my talk, so yes, I'll get to that, yes. Okay, so these are the single trace fields. Okay, we have this map. And so I was saying this will form some kind of an algebra. This is going to be essentially, it's a free theory, so it'll be essentially determined by Wick contractions for some two-point function that you give. And it's important that this is not an algebra. Okay, there's no sense in which this is an algebra. But I can always find a representative like this. I can always write a representative. And that's what allows me to take the large n limit. Yes?
The single trace algebra is at n equals infinity. So the relevant Hilbert space is that of an n equals infinity CFD. Is that a thing?
Yeah, so I'm going to construct the Hilbert space as was advocated in this paper using the GNS construction. So I'm just going to have an algebra. It's a C-star algebra technically. And then I'll construct from that a Hilbert space. Yeah, so it'll come out.
There's no Hamiltonian, right? Or is there? You don't need that.
Yeah, there's no Hamiltonian. Yeah, don't need that.
There is, right? It's the integral of the single trace operator.
The integral of the stress tensor, it's not clear that survives, but yes.
How can that not survive?
Well, okay, it depends which state in the theory. Yes, it does survive for the vacuum sector. I'm sorry. Yeah, of course it does. Yeah, it's there. Yes, yeah, there's a Hamiltonian. Yeah, it depends. There's some details, but yeah.
Okay.
Yeah. So good. So one thing I'm going to do is this is really the following, because I'm going to put my like algebraic quantum field theory hat on. This is really what I should really do is I should take these guys, exponentiate them, and integrate them. And now I can integrate them over some local region O, right? Some causally complete region O. So, and I can do the same for these guys. Phi integral O phi alpha. Right, and this set just means the set of all of these. With all possible, I mean, there's some function here, there's some function, and so forth. And then there's some map. Okay. And then I'll also just think of these, I'll write these just as Wn, say WnI and Wi. Okay. All right, so this is the single trace algebra. So the next thing I need is a family of states, or a sequence of states. And I'll take these just to be vectors in the Hilbert space. But in general, you can think about mixed states and so forth. Just for simplicity, I'll do that now. Yes?
If
map isn't going to be one-to-one, right? So, I mean, for small n.
Yeah, so it will have a kernel, yes, yes.
And is there something you're assuming about how it becomes more one-to-one as n becomes r?
Yes, you'll see that, yes, you'll see that. So this sequence of states has some property. It has the property that I can take the large n limit. So this is not all states are going to satisfy this. This is part of the assumption. Okay, so what is it? Well, in terms of these operators here, they're called Weyl operators, so I'll use that name. In terms of these Weyl operators, the exponential things, it satisfies the following property, such that, or this is by assumption, the limit on n, psi n, wn1, wnk, psi n, is some state. So what do I mean by that? Well, it's just a way of assigning numbers to these polynomials in W. So this is a state in the sort of the linear functional algebraic sense of the term. So it's just taking these operators to numbers, right? So sigma takes these operators to complex numbers, okay? Now I expect it to be positive, but that's something that will come out. Okay, so good. So once I have this, now I can add some things to this list. So W, the set of W, this thing here, has a natural, has a natural algebraic structure. Once you've given me this state, then there's a natural algebraic structure on it, and then I define C as the span of these W's, right? Okay. The linear span, right? So I just take they're linearly independent, so I just take their linear span, and that's what I call my algebra C. Now, one important thing here is that this also has what's called a net structure, which is this thing over causal regions I can assign different algebras, right? Just like my Mn, just like Mn O. And that just comes from this restriction on this integral to this region O. Yes? Yeah.
The W's are just these e to the I times phi's, right?
Yeah.
Okay. And on the left, the WNs they're not going to, they don't form an algebra.
No.
So you're discussing the W's on the right?
Yes, yes,
But,
yes.
but you're not taking product of them? You're just taking linear combinations? Or
yeah, so the product is kind of trivial for the Weyl algebra. If I take two, I get another one. Right.
Oh,
so there's a product structure on it, but it's kind of trivial, so yeah.
I see. So that's already included.
It's already included once I give it this algebraic structure. Correct. Yeah. Okay, so once I do that, sigma actually genuinely becomes a linear functional on C. And so this is, again, what we mean by a state. It's a positive linear functional. And I can extend gamma n also linearly using the same trick. And what does gamma n do? Well, it maps C of O to Mn of O. Okay, so it's consistent with this net structure, the O structure. Okay, good. So this is a map on algebras. That's what comes out of this. Okay, and then finally, following LL, we can take this linear functional sigma and we can construct a Hilbert space. This is using something called the GNS representation, the GNS construction, the details of which I'm not going to go into, but basically it gives you a Hilbert space and a vector on that Hilbert space that I'll call eta, such that sigma is just the expectation value in that state, it's eta. Okay. All right. So the final thing that I need, so there's a lot of definitions here, I'm sorry. I'm going to condense it. I'm going to give you a whole bunch of things, then I'm going to condense it, and you can sort of forget what I told you if you like. It's a one definition. the final thing that I need is some kind of code, right? So remember in the original setting, I had some isometric operator between h and kappa. I'm not actually going to give it, it's already here, right? So I'm just going to use the structure that I've given you and define a map. Okay, so how do I do that? Well, I just use this equation. So Vn C eta is, by definition, gamma n C psi n. Right, so this, in some sense, is the limit of psi n, in some sense, in the single trace sense. And I'm just defining the map to satisfy this. Now, okay, you might ask why. Right, so this defines the operator because it defines on all states in the Hilbert space. You might ask why. Well, you can observe then that it has the following property. The following limit is true. If I just take expectation values of Vn dagger Vn, I get phi 1, phi 2. And also, if I take limit n, using the definition of the state and the property of the state of phi 1, Vn dagger, gamma n, C1, Ck, phi 2, this is just phi 1, C1, Ck, phi 2. Okay. So this is starting to look a little bit like error correction itself, or the solution to error correction. So in particular, okay, let me not bore you with the assumptions. But there's some technical assumptions that come at this point. I'm not going to mention them. You can ask me later. But you should think of this thing here is basically a statement that gamma n map gamma n is asymptotically a homomorphism. So what is a homomorphism? It's something that preserves the algebra and something that typically comes out of quantum error correction. So if I have C1, C2, this is a homomorphism. At finite n, it's certainly not true. In the limiting sense, it is true. Okay? So this is, preserves the algebra of the C's. Okay. Okay, so physically, this is just, it's only an algebra when n is infinity. At finite n, it's not, and that's what we expect of the single trace sector. Also, this other equation that I wrote is also quite interesting. This Vn dagger Vn equation is telling us that this code is what's called weakly isometric. It means that it behaves like the identity operator in states that I fixed beforehand. So I give you two states, phi 1, phi 2, and you take this limit, it behaves like the identity operator. So it will not behave like the identity operator if I also let the states vary, right? So if I did something like this, I let these states in the Hilbert space H vary, then this would not limit to the same, it's the limit of this guy. Of course, they're still varying, but these limits wouldn't be the same. Okay? So it's only isometric in this sort of weak sense. Okay. All right, so I've given you a lot of stuff to remember. But what I'm going to do is I'm just going to summarize this with a definition. Okay, so this is a code that I'm going to give a name. And then I'm going to study it, right? And of course, I think it's motivated. I did make some technical assumptions that I can't prove. But I think it's well motivated. Well, I will show you that it's enough by doing error correction with it. It's sufficient. I think it's interesting. Physically, I don't have a strong thing to say here, but it is interesting that this is not true. Sorry, this is not true. And so it's not really isometric. And at any fixed n, it will not be isometric. And I think that's an interesting thing because people are playing around with these non-isometric codes. We heard a talk from Daniel last week about non-isometric codes for black hole information. And it seems to be coming out here just generically. Now, maybe how much non-isometric it is depends on the details, but yeah. Yes?
Two questions, sorry. The first one is, if I'm not worried about technical issues, could I just pretend you never talked about the algebra of while operators and just stick with the original von Neumann?
Yeah, good. So I motivated it using these while algebras. These states are free, but this formalism doesn't need that. Okay. So the thing that I'm going to tell you doesn't need that it's a free theory in the bulk. Okay. I think that's also kind of interesting. Okay. But I can't really derive it in that case, but it's still, yeah.
And also, sorry, this is a basic question, but based on the definition of your VN map, how come you don't need an extra copy of VN for every gamma that you put into that correlation function, just based on the definition?
What do you mean every gamma?
So you have like a correlation function with like gamma n of C1 up to CK.
And this equation?
It looks like, it just naively looks like you would get a VN for each of those gammas.
Yeah, I guess it would. That's the definition I'm using, and the property that you're getting at is that it's this homomorphism. And if it's the homomorphism, then it'll be okay, but so it asymptotically is. Okay. So I guess I could have used a different definition, but asymptotically it would be the same.
Okay.
Yes.
Another question.
Sorry, I didn't understand the point earlier that was made about the map gamma not being one-to-one. Why is that?
It's just because, this is like the infinite n theory, and I'm trying to embed like a finite n theory. The infinite n theory into the finite n theory. So it's quite reasonable that gamma n will have a kernel. I don't know, I can't give you the operator that is the kernel, but I expect it will.
I was also confused maybe, why isn't that gamma without the n subscript the identity? Like you took the n goes to infinity limit.
Yeah.
It's not just the gamma.
You just want it to be the identity? Well, yeah, it's because it's not really defined on the same Hilbert space. It's defined on a different Hilbert space. Yeah. But yeah, it's kind of looking like the identity, but it's not, yeah.
Okay.
Yeah. You're right. Okay, so good. So I'm going to give this a name. It's the name of the talk, Asymptotically Isometric Codes. Is the following structure.
Sorry, Tom, can I just, before you do that, can you kind of just give us a sense of like, what's a sequence of states you could construct where it fails to be an isometry all along the sequence? Like, does that have to involve black holes, or can we come up with some sequence just involving, particles in ADS?
I suspect it's true in ADS too, because I'm trying to embed effective quantum field theory in ADS in the finite end theory. So when you strictly try to do that, this is what's coming out of that, by the way, then I think it's going to be non-isometric.
I mean, I guess the issue is because you're allowing yourself to, in the finite end theory, I guess the states where you get into trouble, I would have thought those are states where you uncover trace relations or something, right?
Yeah.
But I thought to see those, you kind of have to make black holes or something.
Yeah, I think that's right. Yeah, so they're like black hole states. I mean,
okay, so that's what I was trying to get.
I think so.
I feel like they kind of maybe need to be black hole states or something.
To see the non-isometric things?
To see the non-isometric.
Yeah, I think so, yeah.
There would be states that contain many particles, right? Many bulk particles?
Yeah, like n of those particles.
But order n bulk particles, right? Or something.
Yeah, there would be states that find G Newton that will collapse to black holes.
Yeah.
They are not black hole states because he doesn't contain.
Well, they're not in the limit. In the limit, they're not. But like.
Yeah.
That's right.
Exactly.
And they will. Yeah.
Yeah, so one thing I forgot to say is this K, of course, is finite. So it's important that I don't have n copies up to n, this doesn't depend on n, it's just finite. Of course, it could be arbitrarily large, it's just finite. Okay, good.
Sorry, Tom. It can't be like The limit that n goes to infinity. Like it seems like the issue is only if you consider something that scales like n to some positive power greater than 1.
Oh, I see what you're saying. I don't know. Yeah, I haven't thought about that. I'm strictly fixing to finite. So you might be able to do better. Yeah.
Okay.
You would have to worry about small black holes.
Yeah, you'd have to worry about small black holes. Maybe less than n to the 1/4 is okay.
Okay, so the asymptotic isometric code is a triple. It's three things. It's this, and this. Gamma n, Vn, and C. Okay, so C, just to summarize, C is this local net. Where the assignment is to boundary causal regions, O. Gamma n are these maps. And okay, here's the assumption. I'll write it. You can ask me what it is later. Uniformly bounded, uniformly completely bounded star maps. Okay, that's just to give it a little bit of structure. It turns out that it need not be a quantum channel. So, quantum channels are the nice things, but in the same sense that this need not be an isometry, it need not be a quantum channel. And in fact, the naive definitions that I've given you above for how to do this map give you something that is provably not a quantum channel. But I need to give it some structure, so that's the structure I'm giving. Okay, and then Vn are just bounded operators between H and kappa n. And then we have the two conditions, which I basically said here. I'll just write again. I'll write them here. The weak operator limit of Vn dagger Vn is 1. So that's how you write that. That statement that that's there. And the strong operator limit, sorry, this is a bit technical. Vn C is 0. And this, although not obvious, is equivalent to this homomorphism property that I just said here. Okay? I mean, it's not unobvious, but yeah. And so, the weak operator limit is where you take matrix elements. The strong operator limit is where I take the operator psi and I compute its norm, and I send that to 0 for any state psi. Okay, it's just a different kind of limit. Okay. Okay, so that's it. So this is the structure. This is asymptotic isometric code, and I want to study it now. Okay, and I want to study it from a sort of quantum era ADS CFT point of view. Yeah, I should say, it was important that I had a state to begin with to take this large n limit, and I've dropped that here. I haven't specified a state at all. I, of course, have a Hilbert space. I probably should have put that in there. But basically, I could use any state in this Hilbert space to construct this code. So it doesn't really matter which one you use. Okay, so that's sort of expressed in this. Okay, so let's say some physically. As you might have already guessed, I call this C for a reason. C will be the causal wedge. There is one property that I forgot to mention that comes out of this vile algebra discussion, is that it's additive. It's an additive algebra. What does that mean? If I take my causal region and I construct it by union of other causal regions, a finite number, it doesn't really matter, then the algebra should be generated by those regions. Okay, that's what it means to be additive. And that's a property of this algebra, and it's something that you expect of the causal wedge. So that's sort of motivation for that. In that case, gamma n are simple reconstruction maps. These are sort of the error correction reconstruction maps, and that comes from this equation here. This is doing sort of error correction. It's basically I give you an operator in the bulk, and you can represent it on the boundary, and that's what the error correction statement is. And it works, but it only works for simple operators. Right, and then we have the map Vn. Okay, so that's kind of important. And another important thing is that this has errors. This code has errors. Okay, but they're kind of interesting kinds of errors. It's maybe not the traditional sense in which you have errors in your sort of error. Sorry, what am I trying to say? Yeah, errors in your quantum error correcting code. So, in particular, because of this feature, there are some states, like these black hole states we were just discussing, where this will fail completely at 100% level, right? But then it's exact in the limit, okay? And that's the thing that allows us to do a lot of things here. So this is errors at fixed n. Okay, and then the most interesting thing to me here is the following possibility. Well, okay, so one interesting thing is that C, of course, can be type 3. There's nothing that stops that, and I expect it will be, typically. And then C will also not necessarily satisfy Hague duality. So remember this sort of property that I demanded of the boundary theory? So in general, causality will demand that the causal wedge of O prime will be contained in the commutant of this algebra. But it won't necessarily demand equality. And actually we'll derive this from quantum error correction, this constraint, but we won't necessarily derive equality. And so what is the picture? Well, it's the usual picture of the causal wedge, say. Which is the following. If I have two regions, O on the boundary, O prime, just represented by some spatial slice, then the causal, if there's some like black hole or maybe even just a star in the bulk of ADS, and I base my large N limit on that sequence of states, then this might be the causal wedge of O, and it need not be the same or the commutant of this, of O prime. Okay, so this is this possibility that you don't have equality here. Okay, and so that allows for non-trivial entanglement wedge reconstruction. So, okay. And so I think that's the most interesting thing, that possibility arose in this code. So now, to proceed, what I'm going to try to do is extend this code further and further out here. But to do that, I need an assumption. It's not just going to automatically happen. The code has to satisfy some nice, some properties for that to be the case. But I'm going to derive for you, I'm going to write down some assumptions where that's true, and that these assumptions are related to quantum error correction.
So Tom, just FYI, you should aim for 10 more minutes since you asked for guidance.
Yeah, okay, that's fine. No, it's not. Okay. Okay, but the claim is that, so I'm going to do error correction and this sort of picture of complementary recovery that was developed by various people, Harlow, DHW, etc., survives the large N limit. You can still do quantum error correction. And this is sort of non-trivial, I think. And it uses some, yeah, I think it's, okay. So following this approach, I'm going to derive some theorem that says that certain things are equivalent. So let me write it here. So I'm going to think about, I'm trying to extend C. So I'll think about another algebra N. It's just somewhere in here, okay? And so this is N pertaining to O, the boundary region O. So the following are equivalent. First thing is there's a sequence of reconstruction maps, beta N, that are actually quantum channels. So completely positive, etc. that do error correction. So I take the limit, and they do exact error correction in the limit. So beta n of n, Vn minus Vnn is 0. So, give me a bulk operator in this region n, and I can give you a boundary operator that just acts on this region and does what it should do on that state, on all states in the code subspace. Okay, so there's that. That's an assumption, but this is equivalent to the following. The other things are two. The same statement replaced with the gamma n, properties of the gamma n map. So remember I told you they didn't need to be a quantum channel? Well, I could just make the same statement without them being a quantum channel, and I still get this equivalence here. So you can basically take these maps and replace them with a quantum channel. And the third thing is for all bounded sequences of operators in the commutant, the following limit holds. Limit on n. Okay, so what is this? This is essentially the nil-Laflamme condition of error correction. So basically, you can think of the commutant region as the errors, and if I project the errors to the code subspace, they commute with the algebra of interest. Okay? Okay, so these three things are equivalent. Okay, and I should say a few things about, I guess, how it's derived, but essentially this is a version of this privacy correctability that Monica referenced before. And I have made an assumption that I'm going to point out to derive this, is that the algebras in question, n, is hyperfinite. What does that mean? Well, it means that it's generated by finite dimensional algebras. There's a sequence of finite dimensional algebras that grows and becomes that algebra. And it turns out that quantum field theory algebras are of this property. Type 3, 1. We actually, when we say this, it's type 3, 1, it's actually type 3, 1 hyperfinite. Okay? So this is good to go. But I needed that assumption to derive this. And you can sort of guess how I derived it. You basically, you project to the finite dimensional subspace, and you do error correction in that. You just follow what other people have done, and you just make sure you can take the limit. Okay, good. All right, so now the nice thing about this theorem is it gives a causal structure to the extension. So now we can prove all sorts of nice results that we expect. Okay. That we might have expected.
Sorry, Tom, should I still be thinking about this in terms of the causal wedge, or have you now,
I'm trying to extend the causal wedge. So
how are you extending it?
I'm just by assumption. So I'm just saying, let's suppose I can do error correction in this larger region, then okay, then it's equivalent to these conditions.
Yeah. So this is some decoupling theorem, but you haven't yet told us the theorem that relates this like to relative entropy or something.
Yeah, it's kind of like, I don't expect all large NCFTs to have a gravitational dual.
Yeah.
So I think there's certainly something here that I have to put in, but it's the same thing that you had to put in when you did error. I mean, there's some error correction assumption that it.
Yeah, I know, but I would have thought that one way of phrasing that would have sounded like more like QES than any of your three do, right?
Yeah. So I won't get to QES, I'll get to JLMS.
Yeah, that's
yes.
what I mean.
I will get to
relative entropy,
JLMS,
yeah.
yes, thank you. Sorry, yeah. You're right, I'm just going through this. I don't know, maybe I shouldn't have done it this way. You can write my talk next time. Okay, so what do you get out of this? Well, okay, yeah, there's some obvious things. Let me just mention one. If n, okay, sorry, good. Yes. So if this is true, any of these are true, I'm going to write the following symbol. n is reconstructible in O. That's what this means. So n is reconstructible from O. So if n1 and n2 are both reconstructible from O, then the union, algebraic union, which is just everything generated by these two, is reconstructible from O. Okay, so that's good, but that means I can sort of define the largest reconstruction wedge by just taking all of them and doing this. And I just take the algebraic union of all of these things that are reconstructible from O, and this is called the reconstruction wedge, I think. Let me call it that. Okay, so the reconstruction wedge has some nice properties that you can derive from this theorem. So this is another theorem. It's interesting enough. The causal wedge is contained in this. This is kind of trivial, but it's true. The other thing is this causality statement is still true. So this isn't quite hard duality yet. And I have things like entanglement wedge nesting and so forth. Okay, so now what we'd like to do is push this reconstruction wedge to saturate this bound. And so that's an assumption. That's an assumption that I can do that. But it's this assumption, I call it assumption of complementary recovery, and I will give you an entropic condition when that happens. Okay, so all right, so complementary recovery is the assumption that epsilon of O prime is the epsilon of O, is basically Hague duality. It is Hague duality. Hague duality. And in this case, we call E of O the entanglement wedge. Of course, now I have to confront the fact that my code has the property that for all states in the code subspace, the entanglement wedge is the same. So I think this is what Chris would call fixed QES subspace. And so that's true, and I'll, if I have time, maybe sort of suggest how we can go beyond the physics of, the limited physics of that. But I think that might be the case, the actual case, when we take this strict large n limit. Okay, so finally, let's characterize this, the existence of an entanglement wedge, using the following theorem, which is that E of O is an entanglement wedge for O if and only if the following limit applies. And this is a little subtle, and I'll gloss over some of the subtleties. If I take the relative entropy with some errors that I'll say a little bit about, between any two states in the code on the boundary, then I should get the relative entropy in the bulk for this region N. Okay, so this is the boundary algebra. If the relative entropy is equal for all states or some class of reasonable states, a dense class of reasonable states in the Hilbert space, then this implies that. Okay, so this is the usual Petz story, and in fact, this is a theorem due to Petz. A slightly modified version of a theorem due to Petz, where he actually studied these sequences of channels. It's not exactly the same, but it's very similar, and so it's useful to have that. And in fact, he indeed uses the Petz map. So the Petz map is the reconstruction map, and it works still asymptotically. You don't need to twirl or anything. Okay, so that's this is JLMS. And you can derive this for this code. Yeah, I should say something about the errors. So the errors is a little bit like this smoothing procedure that you need to do for one-shot quantities. So, yeah.
Tom, you should try to
Yeah.
converge soonish. Approaching the large n limit.
Yes, I am. Okay, so let me just quickly say that to make this statement, you need to include errors. So you basically need to allow for nearby states in this relative entropy, and you need to minimize over the states. So you need to take states that are close in the Hilbert space, say epsilon, and minimize over the relative entropy of these states. You need to do it for both of these, phi and psi. Same thing, phi psi. And this error has to go to 0 as you take n to infinity, but it's important that you have this error. And the reason it's important that you have this error is because relative entropy is not that well behaved under limits. It can jump, and so you need to include that. Now, this is not typically what you do as quantum information people. You wouldn't ever smooth the entropy-like quantities. This is like an Neumann entropy-like quantities. Rather, you smooth the Renyi entropies. But somehow in this limit, you needed to do this. I don't know if that sounds wrong or right, but yeah. Okay, so let me just conclude. I wanted to also say that bulk flow is equal to boundary flow, because I like that, but let me just say that. Modular flow works. And let me just conclude by saying a few words about the stuff that we're missing. So it seems that this code is one of these fixed QES error-correcting codes. It still has a lot of stuff in it, right? Because it has all of bulk quantum field theory in it, but that's okay because I've taken the large n limit to get it. So then how do I propose seeing other things like state-dependent entanglement wedges or state-specific back reaction effects, different entanglement wedges for different states? The proposal is that in the large n limit, the theory splits up into sectors. And each of these sectors has a different large n limit, so you have to use a different sequence of states to define a different thing. And these sectors are orthogonal in the limit. So to each of these sectors, you need a code. You need this thing, this horrendous thing. There's one of these. You need another one over here. You need another one over here. Okay, and then, okay, it's a really interesting question how you patch these together and how it consistently works. But that's the proposal, and yeah, so let me conclude there.
All right, so more questions from the audience? Chris?
Yeah, can you say more about these sectors? Should I understand it's like a different sector for each entanglement, each QES position?
Yeah, I think that's not the only reason you would include sectors, I think, but that is one reason. So I can imagine some examples where that will be the case. I don't know if it's always, the guess is that it's always the case, but I think sector physics is responsible for other things too. So for example, you can try to do this for the thermophile double, and the natural bulk algebra is a type 3-1, and you would get the cross product from this sector physics. There's different sectors that you have to patch together. I think if you just have different bulk geometries, they'll have different sectors. So it's kind of, I guess kind of a mess, but I think it's, if you want to take the strict large n limit like this, it might be necessary.
So for me, it's a bit surprising that you said that you can get this Petz recovery without a twirling, because for any finite n, you still have some potentially small error. And it's kind of known that in the case where there is still an error, you need a twirling. And so you're saying in the limit, this still disappears by this theorem by Ted.
Yeah, so it's kind of astounding
wrong,
to me, but it is astounding. And he used a really subtle property of relative entropy, which I never used before. I mean, relative entropy is upper semi-continuous, but it's actually upper semi-continuous in a very, very weak way. So you just need the states to converge in the weak Banach space dual or something like, there's some math version of this convergence, and that's what happens here, and that's sufficient to get this result.
Okay, thanks.
Yeah.
Yes. So just to clarify, are you subalgebras of finite n and m, or sort of subalgebras of each other?
No. And no. And so, yeah, you might have guessed that you need like there to be like a sequence that has some, and you can try to think that that might work, but it's not obvious. Like, you know, you just have a matrix of different size. It's not obvious that that's a subalgebra or in any sense. And it wasn't ever assumed. Yeah, it would make things a lot easier if you had monotonicity under this flow. So it would be better, but yeah. I'm not assuming that, yeah.
You started by talking about the single trace operators, and you found this nice way to define the causal wedge. And then you had this more abstract notion for the entanglement wedge, but is there a way to, like, can you, like, describe some way to reinterpret the entanglement wedge in terms of some subalgebra operators, the large n limit?
So I think it's just related to the commutants of these things. So somehow you get this algebra from essentially from the GNS construction. So that's something that I sort of gloss over here, but you start with a Weil algebra, then you do the GNS construction. That gives you a von Neumann algebra after you take the double commutant. And it's the commutant there. The commutant of that algebra is somehow the new stuff. It's the entanglement wedge. So it appears just out of that process. I don't really understand it.
But is there like some pedestrian representation of this algebra where it's like,
well,
so instead of just products of like k, like k products of single trace operators where k is independent of n, is there some description of that goes beyond that but gives you the entanglement wedge?
Well, so if we're just talking about the bulk algebra, often the entanglement wedge will be inside the causal wedge of some other thing. Often. I mean, not always, but often. And then yes, then there's a simple thing.
Okay.
Yeah. But it's not always, yeah.
So you define this map C of O that you assign this algebra to the bulk algebra, something that looks like the bulk algebra, to some boundary region.
Yeah.
And you consider those particular boundary regions. Could you consider also a boundary region which is a time-like band in ADS, for example?
Yeah, so I specifically wanted to look at causal wedges. The time-like band, or something like Sam was doing, where exactly the things that Sam was doing. He was taking some time cutoff. That is in the large n limit. So it arises. You can talk about those algebras in the large n limit, in principle. It's not clear it maps to anything in the boundary. In the finite n theory, for example. Yeah, I don't know.
I just maybe didn't understand your construction, but it sounded like you took some operators at finite n, and then you took the limit, right? What would go wrong in the construction if you did that?
If you just restricted
to a time band.
It's
so you define some abstract objects, which are the single trace operators, within this time band. Yeah. And they're all embedded into the finite dimensional Hilbert space for all n's, right? So the map from those single traces to the finite dimensional Hilbert space works.
It works.
The same as what you discussed.
Yeah. It doesn't. Go on. Sorry.
Yeah. So I was just trying to understand where there would be a departure from where you.
Yeah, I think maybe it's true you can do it, but it won't respect locality at the finite n theory. So it won't map to anything nice in the finite n theory, like as in some local region. It'll map to all the to some operator on the full Hilbert space, right?
Yeah, that's fine, but
that's fine.
This would define something which would be you could say is the causal wedge of the boundary region. Of this time-like band.
Yeah. I think it's okay.
Can you just clarify, like, if we want to compare with Monica's talk, like, so there I think, so you would tolerate things that go like 1 over n, right?
Yeah.
In these equations, whereas Monica wants to have something where all the errors are e to the minus n squared. So that's the kind of explains the relative difference in complication, I guess.
So, I just want to take limits, and when you take limits, it could be anything, right?
It could be 1 over log n.
Yeah, it could be 1 over, yeah. So it's true, I'm missing a lot of stuff in that, but yeah.
But I was wondering in particular, because there was this thing you emphasized during Monica's talk about restriction on the bulk algebra, and it seemed like it might have something to do with this type 2, and I was wondering if there's, it sounded like, you said that type 3 would be fine for you, right?
Yeah.
So,
I had to make this hyperfinite assumption. I think that's very similar to Monica's product of type 1 assumption. So it's not, it's different. Okay, it's different. It's very different. But it's an assumption. You have to make some assumption, I think.
Yeah, because maybe this thing of trying to be good to exponentially small corrections may also somehow mix together some of these sectors.
Yeah, that's true. I think, yes, for sector physics, you have to understand a little bit better the errors. So one thing I didn't say, to do this, like prove this theorem, you have like 2 parameters, n, and the finite, like you take n and you approximate it by some finite dimensional algebras, and you take the union, because it's hyperfinite. And so Q is like the dimension of these things, right? And so there's some window where you can do error correction, and you have to stay under that window to prove this theorem. So I think like interesting stuff happens when you go this way. That's sort of Chris and others have worked on. And so it might be interesting to do it from that point of view, take a different limit here. But yeah, like where this curve is, it doesn't, could be exponential, it could be,
Yeah. All right, Monica, let's have this.
You're starting with a single trace operator as a sector. Are you having in mind as a just single trace operator theory, like single trace sector as like a given theory, like n equals 4 super Yang-Mills, or are you thinking of a theory that you can define a closed sector with single trace operators as like a minimal requirement?
The latter, I think, yeah.
Okay. And my second question is that you're saying that hyperfiniteness is like the only requirement here, right? But you're actually utilizing the weak topology, so that can't be the only condition required. You're definitely doing.
I'm using von Neumann algebra, so I'm allowed to take weak limits. Is that?
No, but like, is the restriction only that you're using hyperfinite von Neumann algebra?
Oh yeah, no. I mean,
can't be
yes,
right.
I've made a lot of assumptions defining my code. Yes, those assumptions are still there. Yeah.
Okay, because all right.
Yeah, it's not clear the list of assumptions is smaller than the number of theorems yet, so something to work on.
Okay, those are the questions. But to make a comment, the product of type 1 is very different from a hyperfinite condition. I mean, I used a lot of net qualities and stuff that I did not talk about any subtleties, and the complication is really coming from the fact that I had to deal with the actual different order of n. If I remove that, then I can do it for any generic von Neumann algebras as well. Just that the hyperfinite is a very different condition. It's like it doesn't share any quality.
It's different. Okay, yeah. Okay.
All right, I think we should move on. So let's thank Tom again.